So I think Yishan volunteers to give a question. Yeah, go ahead.
I would appreciate if the step out was your neighborhood.
Sure.
Didn't hear the question, what?
So Yishan would like FLE, so the last talk from yesterday, to be reviewed, and Justin disappeared. Okay, I'm tempted to do it like Sam and Justin way. Like I will give a different construction than like what was explained. Right. Sam, do you want to do it? It's your favorite thing.
Sure.
You do it.
Well, I know what that is something to do.
But you know what I want you to do.
I know what you want me to do. Can you ask for a more specific question?
No, construction of FLE.
Construction of the, yeah, what is that?
Great. Wait, thank you. I have a quick question to that, which is that we just also write what monogram big operas look like for genomes.
Yes, you can. There's a connection. These are connection points on the trivial bundle.
Your real question is what do monodromy free operas look like? And so monodromy for okay. So in the case of GM, so okay. It's related a little bit to this distinction between valence and Winkel operas and Venice operas. So the official Venice operas is okay. These are just connections on the trivial bundle. Full stop.
What is that important?
Why is it important?
What is that important?
Okay, I'll say it. I'm gonna write the monodromy free one. I'm trying to say exactly this just whatever operas are for GM, they're always connections on the trivial bundle. So maybe an exercise in the global context is that if you do global sections of one GM with coefficients and with equal differential operators equal to like you take stack of this, then this is equal to global section building. Let's say like non-directly 0. Which is equal to this operators on the. So that was the sort of quantization of the kitchen interval business. Maybe what you wanted me to say is the set of monoforms. Not important yet, but it's just like that's what connections on the trivial bundle are, so just monoforms. So then there's a question, what do monodromy free operators on the disk look like? So this lives inside of meromorphic operators on the disk. And these are the set of all things of the form D plus omega, where omega is all things of the form D plus f of t dt, where f of t is some Laurent series. And I write K, it's a little bit euphemistic, it really means it's some cumulative ring. Some K algebra, those would be the points. And now what are the monodromy free ones? So these are going to be the set of D plus F's with the property, and F has the same shape as here. It's going to have the property that A minus 1 is an integer, and A minus n is nilpotent for n greater than 1. Assuming I got the inequality. That seems right. So the way this sort of really looks is that this maps to Z by this A minus 1. So that breaks it up as a disjoint union of components indexed by integers. And the way each component looks is it's kind of like components is going to look like the power series, that's covering the A0, A1, A2, A3 times some kind of vector space like formally completed at the origin. So kind of like this mod T inverse K double brackets T. Some just n-affine vector space formally completed at 0. At least in coordinates.
Great exercise line that I could derive that.
Yes.
So what? To actually calculate that answer from the definition. We did okay with the wrong direction.
Right. So like so slightly like the naive statement would be like, no, not gonna do. That's the answer. Linear algebra. Okay, and then there is Ishan's question, which was how do you do this FLE? So let me just give a paradigm for a second. So before we had so remember how we constructed the at least coarse Langlands functor. So I'm just gonna read now for the mod. So there was this spectral action. And then there's this Whittaker coefficient functor. What? This?
Yeah.
Yeah. I had a normalization in my talk and I'm gonna stick with it. Okay, we'll skip that. Coefficient. To the vector spaces, and then you dualize. And that gives rise to a functor even though it goes on from G to the Quadratic of fluxicity check. Dual category, but that's the same as quadratic of fluxicity check. And this was this developing functor is this all course. And so we're going to do something very, very analogous in the local setting. So we have rep G check. Tensor KLG. So this I can map, like I just want to say by convolution, but I'll just say it in slightly more words. So you do this Satake functor to get to this spherical category. KL means spherical level, which will matter in a minute. And then I convolve get to KLG. So that's like step 1 in the arrow above. How does this convolve action work? It works as follows. Not specify crazy analogy here. So the idea is the following. So the loop group acts on this category of representations for Euclid algebra. It's a double concept. That's what that. It's like that. Yeah, exactly. Anymorphism with like the angles off the anyways. Anyone else want to say more words about that?
Yes.
No, but you don't. No, it's a genuine question.
Yes.
Are you asking me in good faith, like as a, or is it as a pedagogical?
It's pedagogical.
Let the people speak up for themselves if they want. Okay.
I am other people and I will say yes.
Amazing. So okay, there's the sort of following okay. Let me just make a comment or thinking in the finite dimensional world. So there's this H to Ram, which is sort of H mostly attacked. And what do I want to say? So for kind of stupid reasons, H to Ram acts on H to Ram H, which is the classifying space of H tap. And so that implies that H to Ram acts in this category of H modules that I was using before. And so what I'm trying to say is there's this general paradigm where groups act on representations of their Lie algebra, there's sort of implicit deriving here, that I'm just gonna leave out. And then this is touched on this, so whenever LG acts on some category C, you think that invariance with respect to L plus G, again, this is just some group subgroup business. This is gonna have this is Tom from these modules on LG on LG C and LG equivariant way, and H no but G the homomorphisms use LG model. So it acts by contrariality. That's all I'm saying, that we have to have contrariality on this C L plus G. So this was this general pancake pattern that I want to say this morning as well. That answer your question, Ryan? So the idea is like just purely by some, it's like it's actually a little bit non-trivial to kind of write out completely in formulas what these symmetries look like of this KL category. It can be done, but it's not just like something it's something a little bit non-obvious, and but the nice thing is from some sort of suitable perspective, it's just completely by some kind of obvious temporality. Like whenever you have this LG acting on this category, you get the spherical action on the spherical part, and this KL designs that you can put the part in for Chinese category. Okay, so at this stage, I have not used anything about critical level. So at some point, I'm going to really mean critical level, but so far, I haven't done anything. I mean, that, like, just, well, yeah. Other questions?
If you're doing K at level K, the spirit category would be at level K.
Right. So these may not exactly see the strategy check. That's a little bit special for integral levels, but okay, John, you're good so far. Okay. So now what we're gonna so that's sort of that's like this analogous to this part of this picture. Now we need something which is analogous to taking the Whittaker coefficient, and that's this functor of Grunfeld-Sokolov reduction. Good. We forgot what that is. This is this thing that gets called. Okay, so ES module M is equal to what's called semi-infinite cohomology of this Ln called plus n coefficients in M tensor by some psi. So psi is a character of this guy. Well, it's like the Whittaker characters. So it sends EI over T maps to 1, everything else maps to 0. And I think of that as really a module structure on K. So when I write tensor psi, it just really means I'm taking the action on M and then I'm slightly modifying the way N acts by saying that these guys act, everything acts the same way it did, except for these particular vectors. I'll add one copy of the identity whenever they add. That's what it is, and then there's the semi-infinite cohomology functor, which is this funny thing that mixes invariance for L plus n and co-invariance for kind of the rest of.
Defined with this thought, rather than this co-limit, like this growth sequence of algebra, but the homology and the tensor of the determined line of set homologous.
Yep.
So it's not a conflict for SL2, which is the first case to understand. It's in that case, it's completely legitimate to take invariance for the algebra homology for the parts. And then that's just in this case, everything we do, then that's absolutely normal subgroups, and you can literally just take homology for the remaining part.
Yeah, like it just acts.
Yeah.
It's a lot. but yeah, in principle, it's like, it's kind of a complicated thing, like, if you start with a complex in degree 0, this goes in both directions, infinitely far in both directions, and you know, there are certain cases where you really can compute it, like on induced modules, like Lynn was saying in his talk, on induced modules, you can compute it. Well, okay, if you induce from L plus n to Ln, and then take the semi-infinite cohomology, it's the same as invariance with respect to L plus n. To give a little bit of a feeling. That's the basic calculation of it. That's the basic trivial calculation of the thing. But there's some non-trivial calculations, which is all of this business about. Well, stubby algebras. What?
Question about the second cohomology. So the definition sort of uses some presentation of LN. Is there like a sort of presentation free way of defining semi-infinite cohomology?
Yes. Okay.
But there's no presentation. No, like it wrote the covenant, so never got which way.
Yeah, it's completely.
And then it's in, you know, throw the algebra, use it as such. If there's economic other ways. You can, there is also an algebra geometric way to do it. In the written, you know, the paper of Lynn, of Sam, whatever the name. Or not methods.
Yeah.
This is also really silly. I know that normally algebras, like, there's just some standard round complex looking thing we write down. But Fagan was the person first introduced this to math, and there's just some standard complex we write down for any of the algebra, which is
Yes.
Including, yeah.
So
Including these infinite dimensions.
yeah.
it's specific to these infinite dimensional ones. I mean, it has the following. You just literally take this. And this is completely canonical given the data we started with, and it really does require sort of this choice. That's why people write this funny L plus n. But you take literally just this complex. So this looks like a Chevrolet complex. Like imagine M is literally just, I mean, it could be a complex, but imagine it's literally a representation. You're going to take this graded vector space where these guys probably have positive degrees and these guys have negative degrees. And you just actually write a differential on this complex. And if you look at what Lynn wrote, like this colimit formula, you'll exactly see something of this shape coming out with some differentials. He just wrote it in a way that was meant to tell you what the differentials are without having to like think about Clifford algebras and things like this. But the way, yeah. But they're very conventional constructions of these things. And let me just say, exactly the same thing works, not just for n, but for g. But in that case, in order to write down the differential, you see kind of obstruction about these central extensions that keep coming up. And that's one of the conventional origins for this critical level and these other kinds of things.
You disagree with people with less.
What did I do? Desecrated. Yeah, that's really horrible. But again, it says don't erase. Yeah. So there's this Drinfeld-Sokolov functor, and just one of the basic things to keep in mind about this Drinfeld-Sokolov functor is it maps the vacuum representation. Okay, put the any kappa, and that's the vacuum representation to what's called the W algebra. That's just the name of the Drinfeld-Sokolov reduction. But this is sort of like this vacuum representation, it kind of has something to do with L plus G, and this W algebra has something to do with L plus of this Cosens. So you can think of this whole game as somehow quantum meaning at the level of filtered algebras, filtered whatevers in term instead of graded ones. It's some kind of version of passing from this from Lie algebra to custom. What was that? This is L plus of G, and this is L plus of what's called the cosine section, which is this F plus B mod n that came up in all the discussions about operators and things like that. This F plus B mod n, let me just say one of the nice things about it is that you can map it to G So the first thing is that it's actually an affine scheme. In fact, it's an affine space. So like you might think this is a stack looking at the formula, but it's not, and acts freely. And the quotient is just some a to the n. And which a to the n is it? It's actually the a to the n that comes up a lot in this business as like the space of characteristic polynomials for the algebra.
So I think you wanted to say this case, which is more relevant. With the really good case, actually signs of two.
Yeah, I will say that. But I will say that I'm trying to give a little bit of a feeling for what the Sternfeld-Sokol of reduction does. No, you're right. Let me say so this W crit is O of operators. O of operand. So this you can think of as something that was sort of designed to quantize this quotient section in some sense, but in a commutative way. That's what all of these, like, people keep writing standard like rational normal forms for like matrices. That's what this quotient section does in a systematic way for all reductive groups, is it tells you kind of like here, like, yeah. There's like you can do a little bit better than writing like this, but if suitably understood, the way this looks is kind of just as a bunch of normal forms for matrices, and since it's mapping isomorphically, I should say, onto this space of characteristic polynomials, sort of invert it and get normal form for matrices.
While we're, let me just say about the opers literally are also a Hamiltonian reduction. There.
Yes.
And everything all that.
No, sorry, they're not. I think they're not literally a Hamiltonian reduction.
Absolutely. The gauge action.
It's the gauge action, but the like, but that's not what a Hamiltonian reduction is. A Hamiltonian reduction is the adjunct action on the dual Lie algebra.
No, it's a bad, but that's not the moment map.
Yeah, the moment map goes to the dual Lie algebra, and the dual, but it's a G equivariant map from some symplectic guy to the dual Lie algebra. G equivariant for the adjunct action on the dual Lie algebra, or adjoint action, the dual Lie algebra, which is not the relevant here.
But let's get it going because some of us need to go.
Some of us need to go. Well, you are welcome to go.
It's better between this guy.
What?
Better between this guy.
Okay. Good so far. So now what I'm going to do is the next step from above, which was to dualize. And I'm going to get a functor now from this KLG into rep G check dual. Well, this is also the same as rep G check. And let me call this maybe DS enhanced, because it's basically like the Sternfeld-Sokol functor, but just slightly smarter. Unlike the previous example here, where this functor is sort of an equivalence up to some mild modifications, this functor, let's say at critical level, is very, very, very much not an equivalence. For example, the vacuum representation here as like these dimensional isomorphisms. Just, I mean, it's just like definitely not an equivalence. Like this, all of these objects are way too big. The Sternfeld-Sokol isn't anything like an equivalence, so that's too bad. But so let me explain how to correct it. So the first thing is I'm going to tell you what this DS enhanced of the vacuum representation is, let's say at critical level.
How about you call this one in subgroup? Because the class will be exactly. There's presentation where the class will be unit.
No, I'll also call it DS enhanced.
But it will be double.
This is like, all right. Okay, I'm gonna take DS enhanced to this vacuum representation at critical level. And I claim that it has the following form. So here, pi is gonna be the name from op reg. G-check. To what's this G-check on the disk, which is a fancy name for PG check. And sorry, it didn't make sense. Pi star of O. And this check right.
Before it was called R.
Both are. This. And this assertion actually deduced from this birth of operas. So the birth of operas, let me just remind whatever it was something about involving these spherical sheaves with the vacuum representation. That was one side. And the other side was something about this map.
Now it's not literally the statement of the law.
It is literally the same in the birth of operas. I mean, that's just what it is.
No, for purposes, it has the convolution on with the vacuum, and then it takes it with DS.
Yes.
If you take vertical.
You're right, it's not literally the birth of operas, but it is immediate from the birth of operas.
Like the flying DS.
Yeah.
To the birth. Yeah. That's good.
And having yeah, okay, so here's what it says. So you take these regular operas. What's an opera again? Okay, main thing to know, they form like an affine space usually, and also they're local systems with extra structure. So then there's a map from these operas down to Wilks's G-check on the disk. Which is just again, forget it, yeah. Now what I'm doing is I'm taking the structure sheet of these regular operas and I'm pushing it forward along this map. I get some like commutative algebra here. And I get some commutative algebra here, which is the same thing as a representation from G-check. And my assertion is that if you take this vacuum representation here. Oh, I see. Yeah. And you push it forward, if you apply this weird Vinval-Topolov functor sort of enhanced version, then you'll get this this thing. And let me just explain sort of why that had to be. So the way this was rigged is that this diagram commutes. So this is functor of G-check invariance. And if you take G-check invariance that push forward to a point, if you push and then push, then you're getting functions on operas, which is also what I'm saying the DS reduction of the vacuum at critical level is. So it is a very consistent picture, it's just slight refinement of the stating kind of story. Proceed? Yeah. Okay. So now let me get this name. Wait, Dennis likes calling this sort of thing RZ. Can I do that? Okay. This is sort of like the regular representation for G-check. It's like if you look at this vector space, like the actual representation you're looking at here, it sort of looks like the regular representation tensor with functions on operas. More precisely, there's like this universal bundle on the space of operas coming from this map, and it's look like functions there. It's like the underlying. Okay, so let me just remind now I have this KLG to this rep G-check, this functor, and it has the property that it sends the vacuum representation, all this is critical level. This is mapping to this RZ. It's not the right functor. Okay. And all of this was like completely canonical stuff we just did, right? So therefore it makes sense factorizably. And so we get an upgraded functor from this KLG to RZ modules factorization in rep G-check. And the basic claim is that this is approximately up to left completion issues. But on plus categories, this is their statement the same as this INTCO on the space of monodromy free operas. And what's the reason for that? So just. So if you were just doing Zmod fact. This would be, again, you put approximately. Info on the space of meromorphic operas. That's kind of this general paradigm we have here. For how you compute factorization modules over something commutative. You take its flat sections over the punctured disk. This is kind of a relative situation where I have something like the space of regular operas, and I'm mapping down to some base. I'm taking factorization modules inside of that base. And so what I'll want are kind of like what you end up seeing is exactly the space of like the sort of the way you compute these factorization modules in this paradigm. If you look at sort of flat maps from here to here that are extended as maps from the disk, here to here, and so that's exactly what this monodromic theory offers us. And so, yeah, so that's the construction of the functor. It's not the construction that Dennis said in his talk, but it's
Equivalent. but like-
it's equivalent.
It's not a mumbo jumbo goes back and. It's equivalent, literally, but like presented in the way it looks.
Yes.
There are reasons, for example, the way I presented. it,
Fine reasons.
it's equivalent. This is a faster way to give a construction. That way you can fix it.
Maybe. Also, at some point, people make aesthetic choices and all that. So yeah. Did that answer the question?
Yeah.
So that's what this FLE functor is it's basically just this functor. But like slightly wrong. Like because of homological spreadsheets. But you can do this sort of favorite renormalization game in the compact scope here. Yeah, the compact scope is this plus category. In fact, the functor's even stat. They really don't. That is really just an equivalence on plus categories, a priori assertion. And then get a renormalization of this category, which is this. Yeah. So like it. Yeah.
It's officially 6, so shall we people have more substantial questions.
Kent had a question. Let's see.
Oh, yeah, one of the questions, like I think one of the statements was made is failed the how to use like B maplets and like Opers also have like components from by maplets.
Yeah.
And like one gets that's the other.
Yes.
Is it, like here from this.
How do you see it? It is a non-trivial assertion. And I don't.
What's the question?
The question is, if you take psi of a vial module, CS of a vial module, functions on lambda regular operas. There have been many updates in the theory of representations at critical levels since the original work of Frenkel and Gates-Corey. I don't think there's any better proof of that than the one that was originally given. So let me just say this. Dennis didn't know what paper it's in. It's Frenkel, Gates-Corey, and it's something like vial modules and operas without monodromy. This might not be exactly the right title, but this is approximately the right title. And it requires really kind of like, I should say, you have to know more about, as far as I'm aware, you have to know more about the Fagan-Frenkel isomorphism than we've said heretofore. So I think it's stuff you know, which is about like relation, that there's a sort of free field picture and some compatibility with the Wakamoto modules is like what characterizes the thing, and you have to really kind of use that in order to do this calculation. It's not just a consequence of sort of Fagan-Frenkel stated as a black box. It was. Yes.
A couple questions. One is very short. How we formally define what is differential operators on the fixer?
Let's say on an algebraic stack. So just like everything, there's a forgetful functor from intco on y to rom to intco on y. Claim it has a left adjoint. And
So is it like full proof of the structure?
Full push of O, yeah, from my guy. Yeah.
Okay, and then I was wondering how, so for this commutative diagram on top, what goes into proving something like this? Like why the limit over, I don't know, like this factorization knowledge, as far as I understand. Okay, is there some limit over a point containing, like subset of points containing?
So let's say it is, so here's basically what Kevin indicated, so like, let's look at the source. So it's really equal star is loop spaces, but like, let's get the rules that you can modify your y, and then you tell you what you go like, so y is like, it's really high. That is an algebra, yeah, and you're allowing. Okay, but what if I just told it, but you can take parts, and then give guys without the full. Allow more and more field, but you can realize that as like by modifying your y at a point. Modify your algebra. Yeah, take the generators of the algebra, but force them multiplying by the uniform x. And
This is the point S or
that's the point x. Okay, you modify the algebra at the point x. Point is that so the entire equal star would be co-limit of arcs that these modified guys. They basically say loops with polar 5 are arcs to the fifth modification.
yes.
And so in the statement that the co-limit of statements were
Yeah, I bound the pole that
but not only bound pole, you realize the bounded pole that arcs to something particular. And then so you reduce the statement to the case of arcs. And in the case of arcs, that's exactly what we have proved.
Just to repeat, so Kevin calculated it on structure sheet with L plus, yeah, just sort of sections over the formal disk. It turns out that's not distinguished at all as a subscheme of all loops. Really, you could have taken any subscheme at all, like polar border 5, and that actually you could have just modified your commutative D algebra so that it had that fiber instead.
Okay, so if I take this algebra instead of sections on X without X, I will get X big without small, we will get that sections global set, like X to Y.
So like you could take this factorization algebra just with the one point. And so that doesn't change this category at all. This factorization module, they only depend on the rarely. If you can define factorization modules without it only depends on the restriction away from the file.
Okay, because it's an algebra, then the model that this, like, sorry, outside of this point, this information gives me
Exactly.
algebra and this one, okay.
The only things you ever see are the restriction away from the point. So this doesn't change. This doesn't change. Both of them only depend on the restriction of the algebra away from that marked point. This also doesn't change. This, well, and really doesn't change. But the one thing that changed is sort of what the distinguished object in here was. So before, the distinguished object was O of this L plus blah blah Y. But now this will get changed to sort of, something that if you're being very legal, you write like this. Like something bigger.
Yes, I understand.
And then exactly the analysis Kevin says, you go through and how to write this out. But as you vary over these bigger and bigger guides, then you get generators.
Yeah, I think my question is actually about statement equal. Like even if I take here,
Yeah, that's a great question, right? And
like is it some sort of
Make it
descent or something?
it's not the same. It's something unusual.
Something that.
But
So like let's recap the state. So you have a scheme, a fine scheme.
yes,
So the thing with calling, you want to calculate the states with horizontal sections.
yes.
How do you do it? Or do you?
I mean, I could imagine covering it by something, I don't know, with them understanding.
No, it's very different. And the claim is the following, that you take this algebra functions, to D algebra, you pull the factorization algebra out of it. So,
Yeah, they say it works.
so,
But why does it work?
why does this work?
Suppose X is zero at the division. That's fine.
Well, that might work.
So it's very easy, I mean, the hands-on way of saying it is that it's very easy to calculate for free things. For free thing, like you
It's like for the handshake.
you take the symmetric
Yeah.
algebra on the cohomology.
And then I formulate.
Yeah,
Okay.
So you have to know how to calculate calculation probability for three things, but that's also easy.
Like it's a doable test.
It's a doable exercise. However, there's also even slicker way to do it.
Yeah.
So let me try to say. Let me just look at just one, really one line.
So here it was like an unusual equivalence. So y will be any scheme whatsoever, in this case like x. So you consider d modules on x, and you consider commutative algebras inside the POM of that. That's one category to consider. And another category is consider factorization algebras, unitary. On x, we introduce those, yeah. And consider, and it's a symmetrical number category under just point and spot. We could take two set, multiply, and consider commutative algebras itself. We made nothing prevents you. So now there is an obvious sample computer here just restricted to that.
Like S inside.
X in the Shandron space. So we have to expect this part of the raw magic, but this is like focus. So you have uniquely, if you can uniquely canonically extend the algebra to primitive factorization off. Now we have this like x and y. So now I claim this if you now there's a so now we'll get to go this. So interesting. Now the way so what we did in this expert the point though, right? There's a more general case why one method to y two and slightly more intuitive. Suppose if I y1 map into y2. So there is a functor d mod y2 upper sheet to d mod y1. Take upper sheet. This functor is symmetric modular. So this functor I'll be erasing piecemeal. So this functor is symmetric modular gives rise to pullback functor. Sorry, com of d mod y2 to com d mod y1. So in other words, we have this forgetful functor. So there is a functor that's pulled back, then you pull back into a functor from com or here, which can use to forget com. Now, suppose the Morpheus match was proper. In this case, so your functor upper sheet admits left adjoint, even with a lower sheet. So the claim is that you still have you do have a functor like the development, which is left adjoint that functor, but this it does not make this diagram commute. It's not compatible with forgetting functor to D1. In other words, if you start with the commutative algebra with D1, commutative algebra D1 is y1, forget it down to just plain D1 to take treat derivative. This will not have a commutative algebra structure. What it does commute with is the functor of the left adjoint. So here it was a forget functor for com that the line category, the functor of symmetric algebra. That would so like this, so therefore you don't know how to fully exist, you don't know how to play. If you stare at this part of equivalence, that becomes really so plain is you can consider com back d1 com fact y1 the naive the Rakish functor with respect to the f sub 1
provide the left adjoints to our sheet. If you work in the run space, you have,
Dennis, maybe the thing to say is that with push forward on the human or round space is a symmetric amount of time.
yeah, many ways to say it, yeah, sure. I'm saying that if you do on the run space, it will be on the nose. Adjoins to this.
What do you mean by S round? Do you mean right eyes of the round?
Yeah, so like, I mean, factorization outputs, but D modules in the run space, do direct in the run space.
Wait, didn't you, have you done anything so hard?
No, I'm saying that if you consider commute factorization algebras. If you do this direct image. On between the run spaces.
So don't forget on underlying factorization.
Yeah. So this usually direct image function between the run spaces sends commute factorization algebra to commute factorization algebra. So therefore, if you want to calculate this left adjoint. Use this equivalent to go here. On y1, go to y2 and go to the diagonal. And that's what you, when you think when y2 is the point, you see that factorization algebra. Because all we did, we went to one space, we just took on. That's all. So that's a safe proof. Again, this is one action. But
It's like optical ones, this is some version of like saying that the community for Excel pro, pro.
yes. I didn't understand that, I think that's my answer, but.
Yes, it is.
Okay, so guys, I think we should wrap up.
Okay, let me just break them over with the number. So there's two proofs of this kind of assertion. One of them is due to like Johnson and Drinfeld, the other one's the one that is said. The one is due to Johnson and Drinfeld, where should follow this, so you reduce. You reduce to the case where it was exactly like was sort of being discussed of a free algebra, sort of polynomial algebra in the module. That happens to be an involving algebra, it fits into this regime of like.
And they'll be eligible.
Yeah, we haven't said these for something, the way like the Casimir guy is like some kind of developing algebra, this guy's also a developing algebra. These developing algebras, if you kind of understand the theory right, which is what's explained here, it's extremely easy to prove the parallel homology. Like if you just kind of stare at what an developing algebra is.
Technology is the same specification.
Yeah, parallel homology is the same thing, yeah, sorry. It's extremely easy to do what the factorization homology is for developing algebras. At least once you put the thing set up correctly, and that's what's explained here. And it's very, very clean, it's very delightful to read, and they just tell you like, here's how you can do the factorization homology for the guides. I don't think they do the application community of guides in that paper, but they tell you to do those guides. And so you can see it will just essentially be something like pathology in the shape of what these developing algebras technically are. Like in some sense, yeah. You can, in other words, you just write some very explicit formula for the underlying D module on run space of this commutative factorization, blah blah blah, associated with some polynomial thing. You see what that D module is, you take its homology and it's obvious over there, it directs. Yeah.
Yes. 6 right, it should go.
Okay.
So there will be more Q&A lectures for that